Hi, I'm Ethan Burnett. I'm a PhD candidate at CU Boulder studying under Dr. Hans-Peter Schaub, and this presentation talks about satellite relative state uncertainty dynamics in the vicinity of a poorly tracked target object. When maneuvering in the presence of relative state uncertainty, collision is an inherent risk. A lot of people have done work in various techniques and methods for mitigating that risk. There's work in analytic and numerical uncertainty propagation. An analytic example is given by the work of Lee et al. In 2016. This figure down here in the center of the bottom is one of theirs. There's the classical safety ellipse to encircle a given avoidance region, depicted down here in the bottom left. There's active and passive methods explored by Breger, Howe, Holzinger, and other researchers. This work in particular investigates dynamics and control in the vicinity of a target object with an uncertain orbit. A lot of works have covered this, but many tend to assume that accurate relative state tracking exists, thus the effect of the target orbit uncertainty only appears in the target-centered dynamic equations. And this work goes beyond that and explores the case that the target object is weakly or completely unobservable and thus has some uncertain orbit, while the other spacecraft, the Chaser, has a comparatively well-known orbit. And the target-centered relative state in this case is thus uncertain. So in this presentation, I'll talk more about why this particular problem is important, why it's interesting, and what can be done analytically about it. So in this paper, we consider a controllable, well-tracked spacecraft which identifies a target object, but afterwards loses reliable observability. So that's depicted in the top right here. The Chaser spacecraft is moving along and observes the target, but loses track before significantly reducing the relative state uncertainty. The Chaser orbit is assumed well known, but the target orbit cannot be accurately discerned, and we allow up to kilometer scale error. The Chaser spacecraft is also allowed to maneuver, while the target is non-maneuvering. And in this case, it's most convenient to linearize about the non-maneuvering target orbit, even though we don't know where it is. So this figure in the bottom right here illustrates geometrically that if I don't know the target object's orbit accurately, there are two effects. First, the relative range that I assume will obviously be wrong, but also the LVLH frame orientation is also unknown, which causes other problems. And because we linearize about an uncertain orbit, the resulting dynamics have uncertain parameters in the plant matrix. For linear systems with an uncertain parameter alpha in the dynamics, we can compute the sensitivities, which are the derivative of the state with respect to that parameter evaluated on the nominal value of that parameter. Then the sensitivity and the difference between the true and nominal parameter value, those give a deviation, which added to the nominal state propagated using the nominal value of that parameter. When these two things get added together, it gives the true state. And the sensitivities also have their own dynamics given down here, where these matrices are also evaluated on the nominal value of that unknown parameter. So in the case of this problem, again, we assume a target object with an uncertain orbit and neglect the chaser orbit error. So then there are 6 sensitivity state vectors, one for each initial target orbit element, and the true relative state is given as the nominal relative state plus the sensitivity-induced deviations. And note that the distribution of stationary differences in initial target orbit elements is linearly mapped via the sensitivities to the evolving relative state distribution. And in this sense, the sensitivities act as the structure by which the relative state uncertainty propagates. We can obtain the sensitivity dynamics, as discussed before, for which all relevant matrices are evaluated based on some nominal target orbit elements. We can also compute the non-zero initial conditions using the mapping from orbit element differences to the relative state. And this figure on the right here shows how an initial choice of nominal target orbit elements from the uncertainty distribution gives a nominal relative state and its dynamics, the sensitivities and their dynamics, the uncertainty distribution in the initial target elements is only affected by estimation, whereas the nominal relative state and the sensitivities are not affected by estimation. They are, however, influenced by control. And this slide gives some of the sensitivity dynamics. I'm not going to talk about this too much, it's in the paper, but note that there are some unintuitive terms like the control couplings here that's discussed in the paper. There are a few major takeaways from this breakdown of sensitivity dynamics. The relative state uncertainty growth is driven by the sensitivity to the target semi-major axis. The unforced sensitivity behavior is actually solvable analytically, but I didn't explore it here in this work. Due to the mismatch between the nominal and true LVLH frame, the control also influences the sensitivities. So because control influences the sensitivities, and the sensitivities yield the relative state uncertainty distribution, we have this interesting idea of controlling some aspects of the relative state uncertainty distribution in predictable ways using control of the sensitivities. So that's something we test in the paper. In particular, we test control of the planar relative state and the planar sensitivity to target initial argument of latitude. And we do this while also preventing secular growth to target right ascension angle via this out-of-plane control component. And note that the sensitivities are not fully controllable, so we can't influence the relative state uncertainty distribution in whatever way we want without estimation. And that agrees with our understanding of estimation theory. So now on to some numerical simulations. I show 3 example results in this presentation. First, I show how the propagated sensitivities can be used to cheaply compute a large distribution of relative states in the vicinity of an uncertain eccentric target orbit. And that's example 1. Then I show that we can do a similar thing in cases with chaser control, which I just show for the CW system for simplicity. And finally, I have an example for joint control of the planar relative states and a subset of the sensitivities. For each of the three cases, these three tables give the uncertainty distribution in the target elements, nominal initial relative state, and other parameters. So here's the first case. Starting with the select sensitivity plots on the bottom, note that only sensitivity to semi-major axis displays secular drift, while the sensitivity to other elements are periodic. And these sensitivities are linearly multiplied with the initial target orbit element uncertainty distributions, and we very quickly get this result of how the uncertain relative state evolves over time for a sample of, in this case, 1,000 points. And this is done in just a few seconds. And this is depicted in this figure with the origin fixed on the target's true position. And we validate this with Monte Carlo simulation. And we validate that every trajectory sampled from the relative state uncertainty distribution is accurate to sub-centimeter accuracy. Note that this takes much longer to do the Monte Carlo study, but this sensitivity-based uncertainty propagation can easily run on board. Here's the second case with a similar thing, except the sensitivities are also subject to naive relative state control. So we try and control the nominal relative state with no consideration of its effects on the sensitivities or the uncertainty distribution. So we aim to achieve a target-centered relative orbit, but since the target position is uncertain, we end up with these drifting relative orbits of the chaser, which might be a little bit hard to see here. And these are at risk of eventually colliding. But this behavior can be computed using the sensitivities. And note down here that I give some of the sensitivities to the orbit elements, and the colored lines are the sensitivities with control, which almost overlap some dashed lines underneath, representing the behavior of the sensitivities without control. And from this, we learned that significantly influencing the sensitivities would require much more control effort than influencing the relative state. And this will be an important point going forward. And finally, here's the case showing augmented control of the planar state and the selected planar sensitivities. And we achieve the desired results specified in the table from a couple slides ago. So overall, in these studies, I learned that augmented control of the states and sensitivities is it's an interesting idea, but it's not generally a good idea in practice because of the high need for control. If I wanted to maneuver while avoiding the target, it's much easier to just move the entire relative state uncertainty distribution than to significantly affect its shape. And these are the conclusions and major takeaways from this paper. We studied satellite relative motion in the vicinity of a poorly tracked target object. Sensitivity-based uncertainty propagation proved to be a convenient and computationally efficient method of studying uncertainty propagation just in this problem. The sensitivity-propagated relative state samples were validated with Monte Carlo studies and showed accuracy to sub-centimeter levels. Control of the sensitivities was an interesting idea, but it turns out to be costly to implement. And again, it's much easier to move the whole relative state distribution than to influence its shape. And there's also various potential for future work, which I list here. And I'd be happy to answer any questions about this work, either here in this conference or via email. Thank you for your time.